All right, as he said, my name is Michael Miller, and we've been looking into hybrid memory at Rambus, and I want to go through our Proteus platform and tell you how we got there. So we hope to go through some of the goals and the motivations for building our Proteus platform, and then the types of research that we can do with it, or that could be done, and then talk about where we go on from here. You know, we all have heard it all over, all the time about the way data is blowing up, and we need to handle more data faster, less power. And so at Rambus, we decided several years ago to start searching in this space, how we can combine combine memories such that we can reduce the cost performance point. And one of the things that we focused on were the emerging memories. And the one that we picked to start with was flash. Now that's been around for storage, of course, but in the memory realm, it's starting to come into its own. And so we started looking at that a couple of years ago. We wanted this to be a collaboration. We knew that we couldn't do it on our own, and so we have partners along the way with us. In fact, Smart TV is a company that we use for our VIP for OpenCAPI, so we're very happy to have that. So it's nice to have them precede this. And of course, we wanted to look at opportunities besides just flash, but go on to the next one. Did I skip something here? Sorry. All right, so when we got started, we said before we start diving into building a platform, we needed to do a bunch of simulation. And we had a Gem 5 simulator, and we tried a lot of different combinations of DRAM because that's the standard right now against which everything is being measured. And then we put in different latencies for what we thought emerging memories could be or might be in the future. And as you can see here on the first column, oh, well. Excuse me. Am I missing something? All right, thank you. All right, so as you can see in the first column, we ran a bunch of benchmarks, and we pegged the DRAM as a control reference and made it all one. Then we decided to go and say, let's take flash or something similar that has a 3 microsecond read and 100 microsecond write time, and ran that against the same benchmarks. And to no surprise of anyone, it's bad, right? We got up even to 100 times worse than just DRAM. But that wasn't where we were aiming for. We were aiming, how can we improve that? And so we had a couple of techniques that we used, and we were able to get pretty close to DRAM performance, you know, anywhere from 1.1 to 1.7 times worse than DRAM, but at a cost that may be pretty compelling. It was compelling enough for us that we decided to go further with this and to build a platform. But what are these Rambus techniques that we're talking about? There were two main ones that were useful for us. The first one is the write interrupt feature. And typically, in flash especially, you start initiating a write, you have your 100 microseconds of write time going on, and you have a read going to the same block, and you're stuck. You got to wait. But working with a partner, we evaluated the ability to interrupt a write and what that might impact on performance. And so as you can see in our simulations, when we didn't have the write interrupt versus when we did have the write interrupt, we got somewhere around half the time, better, twice the performance with the write interrupt than without it. I didn't generate these charts, so if you try to compare all the charts with the previous one, it may not exactly line up, but these are representative of the hundreds of simulations that we did. So that's on the interruptible write. And then on the right side, we went after DRAM management techniques. So you could call it cache, but it's a little bit more than that. We use DRAM as the front end and flash or our emerging memory as a back end. In this case, over here on these charts, we use a 10 microsecond read and a 100 microsecond write. And with those ratios, we found anywhere from 16 to 1, 16 times the flash versus 1 times the DRAM to 64 to 1, were an area that was compelling. It made it, it had a significant benefit. We designed our board to operate right now at 16 to 1 because we wanted to get the best performance possible. And when you take those two together, and you go back to the previous slide, that's where we get these numbers. And we get, like I said, 1.1 to 1.7. All right, so now we're on to the exciting stuff, at least for me as a hardware designer, is we need to implement this stuff because we think we have a storyline that's worth going after. But we had several criteria that we had to do for this design. The first one is it had to be modular. Again, we want to work with collaborators and not just build a system that's just for us. So we designed something that took a host system. We used a couple different host systems, one straight from IBM and the other one from Wistron, to run the software and the benchmarks. We made a few minor tweaks, I believe, to some of the drivers, but by and large, the software was going to stay the same. And then we had a platform that included several different protocols or blocks in it. Over here we have, of course, our OpenCAPI, which is our initial design. We started with OpenCAPI, though we envisioned being able to use Gen Z or PCIe or something similar in the future to be able to convert that into a common interface. And so as you saw in other designs, AXI4 was our interface that we chose to use. So we have an AXI4 interface, and then we have the hybrid tier manager, which takes the requests from the host and figures out how best to utilize the requests and manage flash and DRAM together. So this is a very high-level diagram to show you that we made it modular. The other thing is that we wanted to limit the changes to the software, and I told you about that already. And then the third thing was we wanted to be flexible for the future, because we don't know exactly what memories we'll be using. We knew we were going to start with flash and DRAM, and so that was the other requirement. So if we go to the Proteus FPGA hardware platform. So the Proteus platform has several main components. It has a Vertex UltraScale plus 9, which is quite large. I think the footprint even supports a 13 as well if we ever felt the need to go larger than that. It has 4 independent DDR4 DIMM slots. And independent means that we have 4 different memory controllers, one for each DIMM. They're not banked together. There is a 5th DIMM that is a subset of that, would be for if you wanted a special, it's still a DDR4 DIMM form factor connector, but it doesn't support DDR4. So you can take any one of those and replace the DIMM, the DDR4 with a custom board, which we did for flash. We built some DDR4 DIMMs with a couple of pieces of flash, and we have an example of that out in the, at the OpenCAPI table. We support several different types of links. We have 3 OpenCAPI links. We have 2 Gen Z connectors. There is a PCIe connector, and we had talked, I'm not sure that we have any other connectors for the high bandwidth. And then we have some onboard memory. It's actually DDR4, not DDR3. That's the purpose there was to allow for scoreboarding, page table management, whatever you may need. You didn't want to pollute the main memory on the Proteus board. And then, of course, we have clocking and power architecture that is quite flexible. So that's what we designed. And this is the hardware level. I believe the next page is when we get down to the FPGA level. And you sort of saw this a couple slides ago, but essentially what we have here for our initial design is we have the OpenCAPI logic. We built our logic to convert it to AXI, and then you have a couple of AXI crossbars. And then in between would be, for the sake of our first design, would be more like a cache controller. But this cache controller is not operating, it's operating focused on the flash as the destination, because that ultimately what we want to do is we want to replace as much DRAM as we can with flash because it's cheaper. And so we're operating on a larger block, like 4K, a 4K page for the cache line size for this design. And the cache controller is really only interested in dealing with interfacing to the DRAM. As far as interfacing to the flash, we have additional block over here that has to manage all the policies associated with flash. For instance, you have wear leveling, you have migration, and you have buffers associated with it so we can bring in and out 4K at a time and sort of keep that out of the way until we have the data. So that's sort of the workhorse in the flash. And so if you ended up having something different, you can replace that with a management protocol for a different type of memory. All right. And of course, being FPGAs, if you decide here we show that we have 4 DRAM controllers and then we have a flash. Well, that's not entirely true. It's a combination of 4. You could have all 4 DRAMs, or you could have 2 DRAMs, 2 flash, or you could have all 4 being separate. You just need to have IP for that would be supported by Xilinx, the Xilinx FPGA. All right. So the possibilities, we talked about it being flexible, and our first go was to make a hybrid flash DDR4 combo, and we are almost done with that. I don't have numbers to put up here, so that's good for me or bad for me, I don't know. But that's still a work in progress, but we do have a demo that we have shown in the past, and I can show tomorrow if you catch me outside near the OpenCAPI booth with DRAM. But we have with a huge FPGA, a lot of room left in the FPGA with the design that we're working on. We envision being able to do near memory compute. We have an OpenCAPI, we have Gen Z. Can we hook those two together, make a switch, make some type of fabric? That would be interesting. Can we hook multiple OpenCAPI machines together to one board, or hook multiple boards together via OpenCAPI, Gen Z? A lot of possibilities there. We've also kicked around what type of software support we could do. Can we use prediction, AI on the host to inform the Proteus platform on what 4K blocks we need to get next? Do we do using history, figure out what we may need next based on patterns? So, as I said, we're in the research. I'm in the as was mentioned, I'm in the research labs at Rambus. This is not a part that we're going to take and sell. It's a platform that we're trying to collaborate with others. So, we mentioned a few things. Right now we're focusing mainly on the memory side of the M1, I believe, on OpenCAPI, but we certainly can see where we would be able to do acceleration as well. And I'm sure there are a lot of people out there who have other ideas that would be interesting. And so if you have an interesting idea and you would like to collaborate, we'd be all ears. And that's whether that's industry or academia. It doesn't matter to us. We want to try to figure out what problems are coming and see if we can't come to solutions that would be beneficial. And I believe that is it. I am happy to take questions if there are any.